So yeah, for the last talk of the conference, we have the pleasure of welcoming Magee from Durham, and he will talk about strong convergence of unitary representations.
Yeah, so thank you very much for the invitation. I'm honored to be here because I'm aware of the reputation of Collège de France. In fact, my wife told me this is the only talk I've given that she was impressed by because she knows Foucault. Yeah, so I'm going to give an overview of a research program. I don't think there are any proofs in this talk. It's about strong convergence of unitary representations. So my setup is I'm going to have an infinite discrete group, gamma. All these examples are interesting, even free groups. A surface group of genus G, which is pi1 of this thing. Well, this guy has 4 holes, so G would be 4. Pi1 of a hyperbolic 3 manifolds, SL3Z, braid groups, and anything you can think of really, but these are the guys that I'm thinking about. Okay, so they're real examples, they're not toy models. Okay, so this is the group of which we'll study its representations. So what happened here? Somehow I'm not allowed to go forwards. Okay, so we're going to study finite dimensional unitary representations of this group, gamma. So UN is the group of n by n complex unitary matrices. And a very ambitious goal would be to understand every finite dimensional unitary representation of gamma. Gamma is a free group, we can't do this, but for general gamma, it's an extremely difficult problem. And people devote their whole research career to try to answer that question. For example, the work of Kronheimer and Mrówka using instanton gauge theory to try to construct 2-dimensional SU2 representations of 3 manifolds. Okay, so that's like far too difficult for me to try to do this. So my goal is different. My goal is to study the set of finite dimensional unitary representations as the dimension of the representation becomes large. So even though I said that it's extremely hard in general, I just wanted to persuade you that it's a good thing to do. So if you start with gamma equals z and you study all its finite dimensional unitary representations, then you learn about the Fourier transform. And then most of us agree that that's a good thing to think about. It's very profitable. If you take gamma to be the Heisenberg group, which is a little bit more complicated, then you're constructing matrix models of quantum mechanics, et cetera, et cetera. So you can view everything I'm talking about as some kind of like grand generalization of these things. Okay. Okay, so so what do we know about representations of groups in general? Like if I give you a complicated group, like SL3Z, what representations does it definitely have? It definitely has the trivial representation. That's finite dimensional because it's one-dimensional. The group does nothing on a line. And then if you want to, you could take direct sums of the trivial representation. I'm not sure why you would find this interesting, but you could do it. So it has n-dimensional representations. Great. And then it always has this infinite dimensional representation, which is called the left regular representation. So the group acts on L2 functions on itself by left translation. This is the formula. Even though my talk is about finite dimensional representations, it turns out that this object shows up again and again. It turns out to often be the right thing to compare finite dimensional representations with. Okay, so we'd like to work with a class of groups that have many representations in between these things, right? And one source of that kind of group is something is residually finite groups. But not only residually finite will show up in my talk, but residually something else. So I'm going to just talk about residual properties of groups now. Okay, so gamma is residually C. C is some class of groups. For example, finite groups, permutation groups, free groups. Gamma is residually finite. If for every gamma in gamma, which is not the identity, there's a homomorphism to some group in your class of groups that doesn't kill that element of gamma. Okay. Now there's an a priori slightly stronger notion, which is being fully residually something, which means that for every finite subset of your group, you can find a homomorphism to something in that class of groups, which injects on that set, or to relate it to the previous definition, doesn't send any of the different set to the identity. Right, so it really is a generalization. Okay, so you can inject on any finite set and map to something in your class of groups. Okay, so just like as just to get our head around the definitions, residually finite is the same thing as being residually Sn. Sn is the group of permutations of 1 to n, because every finite group embeds into Sn, right? And then being fully residually finite is the same thing as being residually finite. Obviously, fully residually finite implies residually finite, but why the other way around? Because products of finite groups are finite, right? And then you can complete the exercise. But residually free is not the same as fully residually free. So I'm aware that some people have essentially seen this talk before. So for these people, a little exercise is this. You can think about this for the rest of the talk, and there's the hint. Okay. Okay. So yeah, residually finite, residually free, fully residually free. The point is that if you have a group that's residually finite, you know it has many interesting finite dimensional representations. So you have many homomorphisms to Sn via whatever finite group you want to think about. You have many homomorphisms phi to Sn, and then you could take any representation of Sn. You probably shouldn't take the trivial representation. That won't give you something interesting. So you should take the first non-trivial representation, which I call the standard representation. The standard representation is, you basically know it. So we know how to represent Sn as 0, 1 matrices, n by n 0, 1 matrices. But this is not irreducible because there's an invariant vector. So you take this one away, and now you have an irreducible n minus 1 dimensional representation. It's very related to what Ramon talked about when he took away the Perron-Frobenius eigenvector. Okay. It's essentially the same thing. And since you're residually finite, you're fully residually finite, and therefore you can take phi to inject on larger and larger sets, that is the sequence of sets eventually exhausting gamma. And by this, you're guaranteed that you obtain essentially different representations, right? And every single example of group I gave you on the first page is residually finite. Okay, so we're very much going to remain in this category. Okay, so what is strong convergence? If I have a sequence of finite dimensional representations of gamma, rho I, they strongly converge to the regular representation if, for every element of the group ring of gamma, the operator norm, okay, so first of all, I extend my representation to a representation of the group ring linearly. And then I ask that when I take the operator norm of rho I of z, it converges to the operator norm of lambda, the regular representation of z. So this is convergence of norms. Now, why did I make things so complicated by introducing the group algebra? Well, if I just wrote gamma, not the group algebra, then rho I of z and lambda gamma of z are unitary, so they both have norm 1. So you can get anything interesting out of this. So you have to make things linear combinations to actually get something interesting if you want to take norms. Right, so the rho I of z end up not being unitary, but they're finite dimensional matrices. All the norms are operator norms. I'm going to give another picture of this in the next slide. And it's not really the subject of the talk, but there's weak convergence as well. Weak convergence replaces norms by traces. In that case, you don't need to go to the group algebra. You can just remain with the group because the trace is linear. Right. That's just in case you're wondering what is weak convergence, but I will explain it a bit more. Okay, so here's the actual picture you should have. So I said gamma z is interesting because you learn about Fourier transform. Okay, so here's the Fourier transform. So if gamma z or any amenable group, here's what it looks like in terms of spectra of operators. So you could take your definition of amenable to be that every finite dimensional unitary representation is weakly contained in the regular representation. So when I look at the spectrum of the finite object that comes from the finite dimensional matrix algebra, it a priori lives inside the spectrum of the limiting object, a priori, just because of what the definition of amenable is. So it lives inside that region to begin with. Strong convergence is asking that the spectrum of the finite guy becomes denser and denser, right? But weak convergence is actually asking that the spectral measures converge. So, okay, you just notice that something's wrong, which is that the weak convergence is stronger than strong convergence. But the solution is that we never think about amenable groups. Okay, so that solves it. There are actually open problems about amenable groups, but I don't think about them. Okay, so what should we think about? What do I want to think about? So here's the picture for non-amenable gamma, which I said you can take it to mean that you don't have this a priori confinement of spectrum. So you can have spectrum of the finite guy like that lives outside the spectrum of the limiting guy, like these guys. What strong convergence tells you is that if you fix an epsilon, this is the epsilon here, and then you look at the region outside epsilon of epsilon neighborhood of the spectrum of the limiting guy, eventually spectra of the finite guy in that region will not happen. In other words, there's no residual spectrum in compact regions outside the spectrum of the limiting guy. So it says there are no residual outliers, or that there's a near optimal spectral gap. So just a technical thing. If the reduced C-star algebra of gamma, which I'll define in a moment, has a unique trace, which is just take it as a property it could or could not have, but it's a property that we not completely understand thanks to work of Breuer, Kalantar, Kennedy, and Ozawa, then strong convergence implies weak convergence, which is nice. Okay, so things are kind of working right for this class of groups. Okay, any questions? Okay, so there's that was like a spectral picture. There's an operator algebras picture as well. So now I define what the reduced C-star algebra is. So the regular representation of an element of gamma is a unitary in the bounded operators on L2 of gamma, right? So you can take the algebra generated by these unitaries, and then you could take a closure in different ways. If you take the norm closure, you get a C-star algebra called the reduced C-star algebra, this thing. All right. This is what strong convergence tells you in operator algebras. So first of all, your sequence, let's say that the rho I converges strongly to lambda gamma. Then you take the product of all these maps. You get a map from the group algebra into the space of bounded sequences with entries in the respective matrix algebras, right? I'm just writing down the list of the image. If I have Z in the group algebra, I just write down the list of the images. And then that's it, okay? And then you can mod out by the sequences that converge to 0. Okay, and this itself is, okay, it should be a C-star algebra, yeah. And the point is that if you have the strong convergence statement, this purple diagonal map, which exists only on the group algebra, it actually extends to the reduced C-star algebra, and it extends to an embedding. Okay. Now, the property by itself that the reduced C-star algebra embeds into here is weaker a priori. That property is called, when that happens, the reduced C-star algebra is called matricial fields. It's due to Blackadar and Kirchberg. This is having strongly convergent unitary representations is more than this, because this only requires that your sequence of maps rho I are approximate representations in the norm sense. Okay, so if you take rho I of A times B and you compare it to rho I of A times rho I of B, and then you take the norm of this should converge to 0 for all A and B. Having approximate, obviously it should be, in principle, it's easier to find approximate representations than true representations. So basically the existence of strongly convergent unitary representations is me asking that the reduced C-star algebra is matricial field, plus that the purple map lifts to an actual map via true representations. Okay, so it's like a strengthening of this matricial field property. Okay, so it's very hard to come up with a good name for this, but we thought about it and tried to come up with something. So we say that gamma is purely matricial fields if there exist actual representations, finite dimensional representations of unitary representations of your group that strongly converge to the regular representation. And if, moreover, the rho I are of this form that we saw coming from residual finiteness, then we say that gamma is purely permutation field. Okay. So these two properties are kind of like extreme points of a range of definitions that you could make. Asking just for finite dimensional unitary representations is pretty loose. And asking for permutation representations of this particular form, like remember, you could have taken any representation of the permutation group, is very strict and hard to achieve. But in between, there are other things. You could just ask that your representation has finite image. And in fact, there is an application of that property, which was developed by Antoine Song. So Antoine Song wanted to answer a question of Yao about whether there exist negatively curved minimal surfaces in Euclidean spheres. And Antoine came up with something which used strong convergence. I think it's fair to say it's a breakthrough work. And he almost answered this question. I'm going to come back to this later. But he only needed to use the property that the representation has finite image, nothing more. Okay, so these are properties that a given discrete group may or may not have. They're like super strengthenings of residual finiteness or being residually linear, which I haven't defined, but okay. In a way which revolves around spectral gap. So the broad question is, which groups have these properties? And it's really mysterious. We don't know. We really don't know. So that's the question about discrete groups, right? But there's a bit more well-known problem, analog of this problem, which is not for discrete groups, but which is for semi-simple Lie groups, like SL2R, PSL2R. Okay, so I'm going to talk about that analogous problem first, just to give more motivation for this. This is like, so my program is like a discrete analog of what I'm about to talk about for 2 slides. Something that happened to the wall. Yeah, I can hold it. So G is a semi-simple Lie group. It's playing the role that gamma used to play. Right. And now here's a question. What should be the analog of finite dimensional unitary representation? The clue, it's not finite dimensional unitary representation because there just won't be very many. Okay, so that's not a good game. The analog, I think, is induced representations from finite covolume lattices. Like that should be the analog of finite dimensional unitary representation. Okay, just go with me. So then choose your favorite adjectives. Arithmetic, co-compact, non-arithmetic, congruence, whatever you like. Do there exist lattices in your semi-simple Lie group with that adjective, whose covolume tends to infinity, and such that the induced representation strongly converges to the regular representation? So in many cases, Langlands and Ramanujan-Peterson tells us the answer. What the answer should be. I mean, it's never actually proved. Okay, so. And sometimes also theory of automorphic forms tells you that there are some obstructions to this. For example, for SL3Z, there are, for congruent subgroups of SL3Z, there are non-tempered Eisenstein series that are going to screw this up. Okay. Yeah, so this is an interesting question, and I don't think anyone's actually written down the complete answer, even the complete answer which is predicted by Langlands. But in one case, we do know the answer. For PSL2R, yes. Now, come the adjectives. For co-compact non-arithmetic and non-co-compact arithmetic lattices, it was done by me and Hyde. And it implied this conjecture we found of Boozer from the 80s, which is that there are compact hyperbolic surfaces with genus tending to infinity and lambda 1, 2, and 1/4. The presence of the adjectives in the above is due to restrictions of the method that we had at the time. Then we worked out that we could get around something and prove for compact arithmetic surfaces. That was done with Hyde and Lauder. I'll come to the purple in a minute. It's even true for Weil-Peterson random surfaces by the breakthrough work of Anantharaman and Monk, and see the follow-up work of Hyde, Massera, and Thomas. And for random covering surfaces, due to these authors. Okay, so you see it's a busy area. These are all from the last few years. And then there's something else you can do, which is that you can guarantee that every point between 0 and 1/4 is a limit point of lambda 1 of arithmetic surfaces. And you can do this for, it's okay. I'm happy to hold. Yeah. And the limit point of compact arithmetic surfaces by Hyde and Bram. Okay, so for PSL2R, we know a lot of things. There is a technicality the way I've discussed things, because most of the time these works talk only about lambda 1, but there's actually other types of representations that can intervene. Like you need to check something about discrete series, but that condition on discrete series will always be satisfied in large genus by Riemann-Roch. Okay, so
this slide is a mixture of random results and
yeah. It's true, but I wanted to mention everything. Right, so yeah, let me say a bit more about that. So there's the question of existence, which I'm focusing on today, and then there's the question about whether the generic representation of a certain type has the property. But I wanted to talk about as many results as I could, right? Especially not mine. Okay. So back to discrete groups and the analog of these questions for discrete groups. So already for free groups, it was a hard problem at the time. I mean, the question was asked for 20 years before it was answered. It was proved by Hagerup and Thorbjornsen that free groups are PMF. That is actually the main theorem of their paper. There were several applications of this to operator algebras. And then later, more recently, Bordenave and Collins proved that finitely generated free groups are PPF. And like Nalini mentions, Bordenave and Collins weren't interested in the existence result. They were interested in the genericity result, like whether it's a generic phenomenon for permutation representations, and this is what they prove. The main interest of their paper is that they prove it in a specific random model rather than existence, but I'm happy that they proved the existence. Both these results use random constructions, and that randomness cannot be removed as of yet, leaving us with an embarrassment that we do not know, even for F2, whether there exists, how to write down, okay, and we're not going to play silly games about writing computer programs. You write down, for me, an explicit sequence of finite dimensional unitary representations of F2 that strongly converge to the regular representation. No one knows how to do this. There are some candidates. I'll not talk about them now. Yeah, the theory of strong convergence of free group representations is extremely well developed, in my opinion. So, yeah, the fundamental theory fundamentally, like Voiculescu is at the start of it because of free probability, right? And then there were important contributions of Lehner, PCA, and others. And then onto random things, there are many random matrix results that prove different types of strong convergence of finite dimensional unitary representations, but it's always random. And okay, you can read the names. Probably, I'm sorry if you're here and your name is not there. I tried. Okay, so I'd like to go beyond free groups as far as possible. The motivation was surface groups, which we'll talk about, but I told you about fully residually free groups. Finitely generated fully residually free groups are called limit groups because they're the groups that act on R trees. Okay. Don't worry about that. It turns out to be like a profitable class of groups to think about. So with Lars-Lauter, we proved that every finitely generated fully residually free group, every limit group is PPF, has the strongest possible approximation property. And the main corollary I was interested in was that most surface groups are limit groups. Not all, but there's only a handful of exceptions, and we could also check those by hand. So we managed to achieve that every surface group is PPF. And then I'm not going to tell you about the proof, but the proof actually proves something more interesting than the result itself. Okay, and I wanted to highlight this. So the actual hard part of the proof is the following statement, that C star red of a limit group embeds into the ultra product of C star red of free groups. Okay, I just said ultra product for the first time. If you didn't like it, take it to be that quotient of L infinity that I talked about before. Okay. And this thing itself turned out to be useful outside the scope of talking about finite dimensional unitary representation. So 4 young guys, Amartam, Gao, Eliavali, and Pachel, were able to go into the proof of this and use it alongside work of Lionel Robert to get this big breakthrough about the reduced C-star algebra of F2. So I thought I'd advertise that. And then I mentioned Antoine Song's big piece of work to try to construct minimal surfaces in Euclidean spheres. And Antoine didn't quite get there, but 4 authors found a way to push Antoine's work over the line in October 2025. So that's Ancona, Laborie, Rogue Sanchez, and Toulis. And they fully resolved Yao's question, right? That there exist negatively curved minimal surfaces in Euclidean spheres of sufficiently high dimension. And they use corollary 4 as an essential step. Okay. Okay, we know about limit groups. The next class of groups I want to talk about are right-angled Artin groups, and I'll tell you why first. So I wasn't interested in right-angled Artin groups from the beginning, but I was interested in hyperbolic 3-manifold groups. So there's a bunch of deep work, which is on the next slide, which tells you that every hyperbolic 3-manifold group virtually embeds into a right-angled Artin group. And this somehow works perfectly with the following facts. The property of being PMF passes to finite index overgroups and arbitrary subgroups. So that means whatever you prove PMF for RAGs, you prove it for everything which virtually embeds into a RAG. And it turns out, for some reason, that many groups virtually embed into RAGs. So proving for RAGs is a very good idea for this reason. Now, I could motivate it a different way by saying that RAGs, and what is a RAG, sorry? RAG has a presentation that you have some generators, and the only relators are some pairs of those generators commute. You can say it in terms of a graph if you want, but that's it. So motivated by the bottom thing, with Joe Thomas, we proved that every finitely generated RAG is PMF. Now, I would like the stronger property PPF, but it's not true for RAGs. RAGs are not PPF in general. So I proved it's a smallish proposition that F2 cross F2 cross F2, which is a RAG, is not PPF. And this used to be called, okay, I said 3-2-1 problem. So there used to be a problem called 1-2-3 problem, but then Jayadev told me, he's asleep, Jayadev told me that 1-2-3 problem was already taken, so I should call 3-2-1 problem. So what is 3-2-1 problem? So F2 cross F2 cross F2 is not PPF. F2 is PPF by Bordenave-Collins, and F2 cross F2 is open. But conjecturally, yes.
You should call 3-1-2 problem.
I can't change it again. Yeah, maybe. It was true that in my talk I called it 1-2-3 problem, and you told me to change. Yeah, F2 cross F2 looks extremely difficult. Okay, so consequences, what we really care about. Every hyperbolic 3-manifold group is PMF, but it goes via this huge body of work, which is Egel, Bergeron-Wise, Kam-Markovich, Hagelin-Wise, and the final Wise is for the non-co-compact case. And that actually is earlier. Okay, and we'd like to get some kind of spectral geometry consequence of this. Unfortunately, we can't prove what I'd really like to prove, which is that there exists a sequence of hyperbolic 3-manifolds with volume tending to infinity and lambda 1 tending to lambda 1 of H3, which is 1. So this is open. Proving PPF would do that. But what do we get if you kind of do what you can? We know there is for any hyperbolic 3-manifold, there is just a sequence of finite dimensional flat Hermitian vector bundles over M whose dimension tends to infinity, and lambda 1 of the natural Laplacian for that vector bundle tends to lambda 1 of H3, which is 1, which is kind of irrelevant, but yeah, lambda 1 of H3 is the important thing. Anything else that virtually embeds into a RAG is PMF. Coxeter groups using a result of Hagelin and Wise. One related groups with torsion, Wise. So suddenly proving this thing for RAGs, it greatly enlarged the class of groups that we know PMF for. which is good. But, okay. Yeah, so this is sad face. Okay, so now SL3Z. So hyperbolic surface groups have many unitary representations. Hyperbolic three-manifold groups still have a lot because you can use unitary representations to come from rags and you can write them down. But then hyperbolic three-manifold groups seem to have, in some sense, less unitary representations than surface groups. Then you go to something like SL3Z, and now it has very few finite-dimensional unitary representations. So it's not very hard if you know by congruent subgroup property plus an epsilon, which can be done in different. That epsilon can be done in different ways. The epsilon is proving that every finite-dimensional unitary representation has a finite index kernel. Okay. Every single finite-dimensional unitary representation of SL3Z arises by reducing SL3Z modulo M, and then taking a representation of SL3Z modulo MZ for some M and some capital N. And you can reduce this in various ways. By Chinese remainder theorem, you can reduce it to prime powers. It doesn't help that much, but yeah. So in principle, for SL3Z, I can write down every single finite-dimensional unitary representation. But the really embarrassing thing is that even being able to write them all down, in principle, we cannot decide whether they strongly converge or not. Like, we don't have a good way to do this. Even if you can write the thing down, like if I write down, take SL3Z, reduce it modulo P, take the regular representation of SL3FP, take away the trivial representation. Okay, this is the most explicit thing in the world. This is Margulis expanders, right? But no one can tell us whether this strongly converge or not. Even if the answer is no, you'd expect if the answer is no, then you could easily see that that doesn't work. But there's no easy certificate of not strongly converging. And somehow SL3Z is not even the worst. Like, this is worse because there's less room to work. You'll see in a minute. So open problems are SL2Z 1 over P for PMF, just the unitary representations. Co-compact lattices in SLNR for N at least 3. There you don't know congruent subgroup property, but you're free to assume it if you want. You still won't be able to. I don't think you'll be able to solve the problem. Okay, or if you do, you'll have a very good paper. Yeah, but it's not really about SL3Z. It's more about this embarrassment of like even having something explicitly written down, not being able to decide the truth or not of the convergence. Okay, but then a happy face. So SL4Z is not PMF. And the proof is completely algebraic. It's the following fact, which has nothing a priori to do with strong convergence. This is joint with Michael de la Salle. Every non-zero finite-dimensional unitary representation of SL4Z has a non-zero SL2Z invariant vector, where SL2Z is that copy of SL2Z. And the proof of this begins with the congruent subgroup property plus epsilon, as I said before. And then there is an element of writing down every possible unitary representation, but it's cleverer than that. Okay, so you sort of, and you reduce to prime powers. But anyway, that's a fact, which has nothing to do with analysis, like a priori. So how does it relate to analysis? Right, so let's say there was a putative sequence of finite-dimensional representations of SL4Z that strongly converged to the regular representation. That strong convergence would pass to any subgroup. So in particular, it would pass to SL2Z. SL2Z is not amenable. So it would tell you that, like if I took my element of the group ring to be the sum of the generators, sum of fixed generators of SL2Z, that element would have a spectral gap in the limit. But actually, there's an SL2Z invariant vector, so you're completely screwed in terms of having a spectral gap. Okay, so that's the contradiction. The problem is that with SL3Z, so it's a funny case where you have a theorem for SL4 but not SL3. And then again, SL2Z is PMF because it has a finite index free subgroup. So it's like a 4-3-2 problem. Okay. SL3Z is open for PMF. And the problem with this approach is that the second theorem is simply false. So there exists an infinite sequence of finite dimensional unitary representations of SL3Zs which have no SL2Z invariant vectors. And in fact have no invariant vectors for any fixed non-amenable subgroup that you can find of SL3Z. Using this particular obstruction to strong convergence is essentially having a non-amenable subgroup with an invariant vector is the only obstacle we actually know how to use. And so once this obstacle fails, for SL3Z, we're screwed. I'm going to finish a bit early, but everyone will be happy. Okay, the second theorem is false in SL3Z, but if we look at SL3Z modulo PZ for primes, it fails to be true, but it only fails to be true for one particular sequence of representations of SL3 FP. So it's like there's this one sequence of representations that could, of SL3Z, let's assume we factor through prime, that could strongly converge to the regular representation. We can write it down in principle, although it's not actually that easy. And we cannot decide. That's it. Yes or no. But we know which sequence of representations it would have to be. Yeah, and that's basically it. This is what I know so far. But there's homework. So yeah, I would be interested in answers of apart from cases where I already told you the answer of the property of these groups. So very rigid groups like SL3Z, SL2Z, 1 over P. I'm quite curious about lattices in F4 minus 20 because it's a bit of an odd case, but it seems quite hard to work with. Any hyperbolic three-manifold group, PPF, because this would give a route to proving this thing about the sequence of hyperbolic three-manifolds with volume tending to infinity and lambda 1 tending to lambda 1 of H3, which is very appealing. You can be very, the thing about hyperbolic three-manifold groups is you can be very explicit about what the group is. So you can take this free bicyclic group where, so it's an extension of F2 by Z, where the F2 acts, wait, is there something weird about this? Yeah, that's exactly right. So it's a figure eight null complement. Okay, I'm not going to try to unpack my notation. So PMF is known by my result with Thomas, but PPF is open. And choose your free bicyclic extension if you want, if it helps you. Complex hyperbolic lattices, I've got no idea. Recently, I got interested in braid groups because there is a machinery of building finite dimensional representations of braid groups, but it does seem like parametric families, but it seems quite hard to work with. And then mapping class groups is just a generalization of that. And the final interesting question, although I'm not sure it's useful to phrase it like this, just a curiosity, is there any property T group that has this approximation property? And that's it. Thanks for listening.